Blockchain security is crucial for safeguarding digital transactions and assets, yet it is increasingly targeted by ransomware attacks exploiting zero-day vulnerabilities. Traditional detection techniques struggle due to the complexity of these exploits and the lack of comprehensive datasets. To address this gap, the UG Ransom dataset provides detailed features for analyzing ransomware and zero-day attacks, including timestamps, attack types, protocols, network flows, and financial impacts in bitcoins. This study leverages the Lazy Predict library to automate machine learning on the UG Ransom dataset, aiming to enhance blockchain security through ransomware detection based on zero-day exploit recognition. By streamlining machine learning model comparisons, Lazy Predict identifies effective algorithms for threat detection. Key features such as timestamps, protocols, and financial data are used to predict anomalies as zero-day threats and to classify known signatures as ransomware. The results demonstrate that machine learning can significantly improve cybersecurity in blockchain environments. The decision tree classifier and extra tree classifier, with their high performance and low training times, are ideal candidates for deployment in real-time threat detection systems. These models can accurately detect ransomware attacks and zero-day exploits, enabling swift response and mitigation. Blockchain networks, which provide a decentralized, immutable ledger, have revolutionized digital transactions, enhancing security and transparency. However, they are not immune to attacks, with ransomware attacks being a significant vulnerability. Zero-day exploits, which involve attacks leveraging previously unknown vulnerabilities, are another critical threat. By developing effective detection techniques, blockchain security can be bolstered against these threats, ensuring the integrity of digital transactions and assets. Blockchain networks face significant vulnerabilities and threats, particularly in the form of zero-day exploits that challenge traditional detection techniques. The complexity of these exploits, combined with a scarcity of comprehensive datasets, hinders effective threat detection and response. Traditional antivirus software and intrusion detection systems are limited in their ability to identify unknown threats, emphasizing the need for robust mechanisms to secure digital transactions. To enhance blockchain security, well-structured datasets with comprehensive features are essential. These datasets should include features for detecting ransomware and zero-day exploits, providing a foundation for improving threat detection and response. Machine learning models offer potential in leveraging these datasets to enhance threat detection and response. By utilizing advanced algorithms and techniques, these models can analyze large datasets efficiently, identifying patterns and anomalies indicative of potential threats. This approach can significantly improve the security of blockchain networks against evolving threats. However, it is crucial to address the limitations and assumptions associated with machine learning models. Overfitting, underfitting, and bias in the training data can lead to inaccuracies in threat detection. Moreover, the continuous evolution of threats necessitates ongoing updates to the datasets and models used for detection. In conclusion, securing blockchain networks requires a multidisciplinary approach, combining cutting-edge technologies such as machine learning with rigorous data collection and analysis. The development of comprehensive datasets and advanced detection mechanisms is critical for enhancing blockchain security and mitigating the risks posed by zero-day exploits and ransomware. The UG Ransom dataset, created by Nkongolo et al. In 2021, is a significant advancement in addressing the limitations of existing datasets for detecting and mitigating threats like ransomware and zero-day attacks in blockchain security. This dataset provides a comprehensive set of features including timestamps, protocols, financial data, attack types, network flows, and IP addresses. These features are specifically designed for analyzing ransomware and zero-day attacks, filling a critical gap in blockchain security datasets. The dataset's ability to track unusual patterns or correlations through timestamps, analyze protocol data for deviations, and provide insights into financial impact and attack types improves the detection and classification of threats compared to existing datasets. The UG Ransom dataset's novel features and comprehensive set make it a valuable tool for advancing blockchain security research, as demonstrated by its utilization in subsequent studies. The paper examines the limitations of existing datasets in blockchain security, particularly for ransomware detection. It highlights the advantages and limitations of datasets like VirusShare and Malware Bazaar, which primarily focus on known malware. The CICIDS and CTU13 datasets are also mentioned, used for network intrusion detection and including various types of attacks. However, these datasets are less effective in addressing blockchain-specific threats. The BTC-ETH dataset provides transaction data from Bitcoin and Ethereum blockchains but lacks detailed annotations related to specific types of attacks. The methodology involves using lazy predict to automate the model selection process, including steps for model training and evaluation. For instance, linear regression is used to minimize the mean squared error, MSE. Machine learning models in lazy predict are evaluated using a range of performance metrics, which provide a comprehensive understanding of their capabilities and limitations. For regression tasks, mean squared error is used to measure the average squared difference between predicted and actual values. Decision trees are evaluated using Gini impurity or entropy, which quantify the degree of randomness or uncertainty in the data. Support vector machines, on the other hand, are optimized using the margin maximization objective, which aims to maximize the distance between the decision boundary and the nearest data points. Cross-validation is a critical technique employed to assess model performance. It involves partitioning the dataset into k-subsets, or folds, and training and evaluating the model k times, each time using a different fold as the validation set. The cross-validation error is computed as the average error across all folds, providing a robust estimate of the model's performance on unseen data. In addition to cross-validation, the study utilizes a range of performance metrics, including accuracy, balanced accuracy, F1 score, and time taken. These metrics provide a detailed understanding of the model's strengths and weaknesses, enabling the selection of the best-performing model for a given task. The model selection process in lazy predict is automated, involving the instantiation of ML models with default parameters, training them on the training data, evaluating them using cross-validation or a validation set, and comparing their performance metrics to select the optimal model. This automation streamlines the process of identifying the most suitable model, ensuring that the best model is chosen for the task at hand. The application of lazy predict to the UG ransom data set automates the evaluation of multiple algorithms, significantly reducing manual effort for initial model experimentation. This streamlined approach assesses the efficiency and effectiveness of each ML model based on evaluation metrics. The dataset includes 17 ransomware families, focusing on features such as network bytes, Bitcoin transactions, threats, addresses, USD transactions, and ports. The correlation between Bitcoin transactions and ransomware incidents suggests tracking Bitcoin transactions can be an effective way to identify and trace ransomware-related financial activities. The correlation with USD transactions implies involvement in financial transactions in USD, either directly or indirectly. Monitoring transactions can aid in identifying unusual patterns indicative of ransomware activity, providing an additional layer of financial analysis for threat detection. Figure 3 illustrates feature correlation using the UG ransom dataset. The results from lazy predict offer a comprehensive overview of the performance of various machine learning models on the UG ransom dataset, as depicted in Figure 4. Each model was evaluated based on accuracy, balanced accuracy, F1 score, and time taken. Notably, the receiver operating characteristic, ROC, metric is absent from the evaluation, which can be attributed to the configuration settings within the lazy predict library. The lazy predict results highlight the performance of different machine learning models on the UG ransom dataset, with accuracy, balanced accuracy, and F1 score serving as key performance indicators. The time taken for each model to execute is also an important consideration. The absence of the ROC metric, however, limits the comprehensive evaluation of the model's performance, as it provides a graphical representation of the trade-off between true positive rates and false positive rates at different thresholds. The discussion on lazy predict results and ROC analysis underscores the significance of considering multiple evaluation metrics when assessing the performance of machine learning models in ransomware detection. The authors computed the receiver operating characteristic, ROC, curve for evaluating the performance of classification models, particularly in distinguishing between classes. This graphical representation shows the model's sensitivity, true positive rate, versus specificity, false positive rate, across different threshold settings. For a comprehensive analysis, the ROC area under the curve, AUC, metric was used to quantify the model's ability to discriminate between positive and negative classes. Given its importance, manually calculating the ROC-AUC for the best-performing models offers deeper insights into their performance in zero-day exploit recognition and ransomware detection in blockchain security. The ROC curve, as shown in Figure 5, provides a visual representation of the trade-off between the true positive rate and false positive rate at different threshold settings. Machine learning models for ransomware detection within blockchain networks were analyzed, and the light GBM classifier emerged as the most effective model, achieving perfect accuracy and F1 score. However, its training time is significantly longer. In contrast, the decision tree classifier and extra tree classifier demonstrate comparable performance with minimal training times, making them highly efficient and valuable in real-time blockchain security applications where rapid detection and response to ransomware attacks are crucial. The model's efficiency in detecting ransomware is evident in Figure 6, which shows their ability to accurately differentiate between zero-day exploits, known ransomware, and synthetic threats. Specifically, they successfully predict 4,748 features as anomalies representing zero-day attacks, which is vital for blockchain security as it allows for the identification of previously unknown threats that traditional detection methods might miss. Furthermore, the models classify 7,455 features as signatures, indicating known ransomware activities and facilitating prompt recognition and response. Additionally, 6,761 features are identified as synthetic signatures, likely representing variations or simulations of known ransomware patterns. This comprehensive detection across various categories underscores the model's robustness and effectiveness in enhancing cybersecurity within blockchain networks. The bagging classifier, an ensemble learning model, exhibits strong performance in identifying anomalies related to zero-day exploits and ransomware activities by leveraging features such as network bytes, BTC transactions, and protocol data. Its quick training times, as depicted in Figure 4, enable frequent updates with new data to maintain effectiveness against evolving threats. In contrast, models like News VC and SVC, although accurate, have prohibitively long training times, making them less practical for real-time applications. The results from Lazy Predict emphasize the importance of balancing accuracy and computational efficiency in selecting machine learning models for ransomware detection in blockchain security. Ensemble learning techniques, with their high performance and low training times, are ideal candidates for deployment in real-time threat detection systems. Calculating and plotting the receiver operating characteristic, ROC, area under the curve, AUC, for these machine learning models will provide a more detailed understanding of their discriminative capabilities. The paper underscores the pivotal role of blockchain networks in securing digital transactions and assets, particularly against ransomware attacks that exploit zero-day vulnerabilities. It highlights the limitations of traditional detection techniques, which struggle with the complexity of these exploits and the lack of comprehensive datasets. The UG ransom dataset bridges this gap by providing detailed features for analyzing ransomware and zero-day attacks. The study leverages the Lazy Predict library to automate machine learning on this dataset, aiming to enhance blockchain security through ransomware detection based on zero-day exploits recognition. The findings indicate that machine learning models can significantly enhance cybersecurity in blockchain environments, with decision tree classifier and extra tree classifier emerging as promising candidates for real-time threat detection systems. The paper provides a comprehensive analysis of ransomware detection and classification using machine learning techniques, specifically focusing on the UG Ransom 2024 dataset. It explores the use of random forest for feature selection and classification, highlighting its effectiveness in identifying ransomware attacks. The study also delves into cybersecurity career requirements, emphasizing the need for multidisciplinary skills in the field. Additionally, the paper discusses blockchain technology and its role in enhancing security, particularly in decentralized networks such as Bitcoin and Ethereum. It touches upon the concept of proof-of-stake blockchains for smart meter data security and their potential to mitigate risks associated with network intrusion detection systems. Furthermore, the paper presents an innovative approach to preventing zero-day vulnerabilities through recursive feature elimination and ensemble learning. The page discusses various studies and datasets related to cybersecurity, focusing on ID systems and ransomware detection. Kannan et al. Conducted a systematic literature review on unraveling ID datasets for enhanced cybersecurity understanding. Al-Hashmi et al. Explored ransomware early detection techniques. Nkongolo et al. Introduced UGransom 1819, a dataset for anomaly detection and zero-day threats. Another study by Nkongolo et al. Presented a cloud-based optimization method using genetic algorithms and ensemble learning for zero-day threat detection. Lastly, Lydia et al. Discussed predicting sepsis disease using random search for hyperparameter tuning based on lazy predict model. These contributions highlight the diversity of research in cybersecurity and its applications.